Hello, welcome to our semiconductor education program. This is Vincent Chang. In this lecture, I'm going to show you the LC-tuned oscillators. LC-tuned oscillators part 1, loop gain derived. So let's focus on how to get the loop gain for this circuit, and also in the end, before the end of the lecture, I'm going to solve the so-called Buckhausen Criterion to get the minimum requirement for start the oscillation and also the frequency of oscillation. So here's the basic structure of the LC-tuned oscillator, which is quite simple. It's composed by two major parts. The first part is an inverting amplifier. How do you know it's an inverting? Assuming the open circuit voltage gain is negative mu. It's negative mu. And Rin is the input impedance of the inverting amplifier. And Rout is the output resistance of the inverting amplifier. Thevenin equivalent. Open circuit voltage gain, negative mu. Inverting amplifier. Equivalent circuit for the inverting amplifier. The second part of the LC-tuned oscillator is the purely reactive circuit. So each element, the Z1, Z2, Z3, is either an inductance or a capacitance. So this is also why it's called LC-tuned oscillator. So now, the first step to understand this circuit, of course, is the model of the sinusoid oscillator and try to get the loop gain and then plug in so-called Buckhausen Criterion. So now you see the blue in contrast with the blue, and the purple corresponds to the purple. The blue part highlight represent the basic amplifier. The amplifier part is the inverting amplifier. And the purple is the frequency selective network. The frequency selective network. So let me give you an assumption, okay? Because in the next lecture, you will see the real circuit, which is the CMOS. So in the CMOS category, in the MOS category, so this assumption is reasonable. It's reasonable because for the MOS, one of the major characteristics for the MOS, the amplifier, is the input resistance is very, very large. So ideally, the resistance between gate and the source looking to gate is infinite. Okay? So let's assume the Rin of the inverting amplifier is very large. So then, during the calculation of the loop gain, we can neglect the loading effect from the input resistance of the inverting amplifier onto the frequency selective network. Okay? So now, it's your job. I encourage you to try to solve this by yourself before you continue the lecture. Let me take out my video, and then you take a screenshot or quickly draw the circuit diagram. Let me ask you, what is the loop gain? Try to find out the expression for the loop gain, okay, of this LC-tuned oscillator. So I give you 5 minutes, try to figure out the loop gain. So let's pause for 5 minutes. It's not challenging, right? So let's quickly go through this. So compared to I think the previous lecture is the active tune oscillator, but the one before the active filter tuned oscillator is the phase shift oscillator. For the phase shift oscillator is much challenging compared to this one. This one is kind of easy. So you can just use the analysis by inspection to solve this. The first part let's start with the aqua. Okay? And going through the inverting and go back to the pink times the factor 1, the first factor, the first loop gain factor. Okay? This symbol represents the pink voltage divided by the aqua voltage equals the factor 1. So what is the factor 1? So factor 1 should be negative mu times denominator. You can write down this on your note. The first item in the denominator is out. So the second item is what? It's the total impedance between the pink and the ground. So what is the total impedance between pink and the ground? You see 2 in series with 3 and then in parallel with 1, right? Right? So that's the denominator. And then put the second term of the denominator onto the numerator, which is the 2 plus 3 in parallel with a 1. Okay, like this. This is what I'm talking about. The first factor. The first factor. And now it's the second factor. For the second factor is easier. So for the second factor, we try to find out aqua's voltage divided by the pink voltage through the so-called frequency selective network. So it's going to be what? A divider. So the denominator is going to be, take notes, R2 plus R2 plus 3. So what's the numerator? 2, right? Like this. So this is factor 2. It's very easy, just divider. So these two together is the expression for loop gain. I hope you get it right. I hope you got this. So now, I said you can restructure and reorganize this expression. So you expand the little bit complicated relations of 2 in series with 3 and then in parallel with the Z1. And then you're going to get this. So now, I said the LC tune oscillator means that each impedance, Z1, 2, 3, is either inductive or capacitive. So this means the frequency selective network is purely reactive. It's purely reactive. It's purely each component's its impedance. Each component's impedance is going to be purely imaginary, right? If the imaginary is positive, then it's inductive. If the imaginary is negative, then it's capacitive. So either capacitive or inductive. It's the purely imaginary, okay? Z1 equals JX1. Z2 equals JX2. Z3 equals JX3. If X is larger than, is positive, that means the inductive. If X is less than 0, is negative, that means the capacitive. So if you plug this into this equation, it's going to turn into the real and imaginary like this. Right? So in the numerator, you see the 2J, that means the negative 1 times negative equals the positive. Okay? So now focus on what? On the imaginary part first. Why? Because now is the time try to meet so-called the Buckhausen Criterion. For oscillator to meet this criterion, Buckhausen Criterion. Let's start with the phase criterion. The Buckhausen phase criterion to eliminate the imaginary part. Let's eliminate the imaginary part. At the frequency of oscillation, the loop gain has to be a real number. So the imaginary part has to be eliminated. But the output resistance is not 0. but the output resistance is not zero, exists. So the sum of the three, X1 to 3, the sum of the individual reactance should become zero. This is the condition to determine the frequency of oscillation for the LC-tuned oscillator. So now, let's move on to the second criterion, which is the Buckhausen magnitude criterion. Buckhausen criterion for magnitude. Then we plug this in at frequency of oscillation. The magnitude of the loop gain should be either greater than or equal to unity. So at the frequency of oscillation, the imaginary, the red highlight, is gone. So what's left? Mu 1, 2, negative 1, parenthesis 2 part 3. So the S1 got canceled out, right? And then what? Then at the frequency of oscillation, what's the negative parenthesis 2 part 3? Look at the purple. Look at the purple. The answer is X1. So mu times 2 divided by 1, mu times X2, numerator. What's the denominator? X1. Should be equal to, should be greater than 1. This just show you negative. The purple just want to remind you, this purple equals X1 at the frequency of oscillation, when oscillation happens. So the mu times X2 divided by X1 greater than or equal to 1. So mu greater than or equal to X1 divided by X2. Get some water. X1 divided by X2. This is the condition for what? The minimum gain to start. Minimum open loop gain to start the oscillation. The minimum open loop gain to start. So oscillation is not random. It's not random. It has to be meet this requirement. To make sure the oscillation will start, you have to satisfy the blue. And the purple will give you what? The frequency of oscillation, which is decided by the frequency selective network. And there is a minimum requirement for the gain of this blue inverting amplifier. This is the major takeaway of this LC-tuned oscillator. In the next lecture, I'm going to show you the two ways of doing this. The first way is more poor, more inductive, which is called a Hartley oscillator. The second way is more poor, the capacitor. It's called the Cobb's oscillator. So see you in the next lecture. Thanks for watching.